Okay, good morning. What on earth are you doing here at 8 o'clock in a spring term? Seriously, right? Well, this is 352. I'm Josh Price. Please look at the syllabus. It's on Learning Suite. We don't have really any time at all to talk about it. The pace of the class is going to be somewhat fast. You expect that in spring. I did the math once, and we need to move basically a chapter a day. So prepare yourself. The class is going to work best if you've read and worked problems before you come to class. Hopefully you've done that in chapter 13. If not, you've got some catching up to do. We'll do our best. Our subject today is basically setting up everything that we'll talk about for the whole first unit, and that is carbonyl chemistry. Hopefully when I say carbonyl, you're used to the idea that we're talking about molecules with carbon-oxygen double bonds. And so we're going to overview their reactivity. If you didn't take 351 from me, you may hear me refer to things that you're not quite sure what I'm talking about. We do talk a little bit about molecular orbital theory in this class. I have an optional sort of study guide to refresh your memory on that on the content page of Learning Suite. If you've taken 351 from me, you've seen this before. In terms of carbonyl reactivity, we're going to focus on carbonyls as electrophiles. And when we're thinking about electrophiles, or in other words, Lewis acids or electron acceptors, we're thinking of molecules that have a low energy, lowest unoccupied molecular orbital, or LUMO. So what is the LUMO of a carbonyl compound? Anybody remember? Pi star, the carbon-oxygen pi star antibonding orbital. If we're looking at our carbonyl as it's drawn here with the carbon-oxygen bond in the plane of the page, actually an sp3 hybridized trigonal planar carbon, all of these bonds are in the plane of the page. The pi star is going to have a node in between the carbon and the oxygen. It's going to have a large lobe on the carbon and a smaller lobe on the oxygen. There will be a node in the plane of the page, which I won't draw, and then lobes of opposite wave function sign below the plane of the page. We'll use color to represent wave function sign. This is how the pi star looks for a carbonyl compound. If, on the other hand, we draw the carbonyl compound on its side from another perspective, with this carbon-oxygen bond in the plane of the page, but the bond between carbon and whatever Y is coming out at us, and the bond between carbon and whatever R is going away from us, and then this represents sort of the plane that carbonyl lies in. This is how the pi star would look like. There would be a large lobe on the carbon and a smaller lobe on the oxygen. The lobes are sort of pointing away from that node in between the two nuclei. And the change in wave function sign is indicated with the different colors. But that's sort of what a pi star looks like. All right? Now, as you may have learned from me in 351, when a nucleophile attacks an electrophile, electrons from the highest occupied molecular orbital on the nucleophile dump into the lowest unoccupied orbital of the electrophile. If that LUMO is an antibonding orbital, as the nucleophile attacks that orbital, the corresponding bond will break. So we expect to see this kind of thing happening with carbonyl chemistry. We expect to see a nucleophile attacking the pi star. It's going to attack the pi star at the carbon for two reasons. First, there's actually more LUMO on the carbon than there is on the oxygen. That's an outcome that comes from MO theory. You can explain it, you can just accept it on faith as a result in this class. The other reason that it attacks at the carbon is because carbon is less electronegative than oxygen. So you expect the bond between carbon and oxygen to be polarized with a partial negative charge on oxygen and a partial positive charge on carbon. And in fact, a third reason is that you can draw a resonance structure in which you have a full positive charge on the carbon and full negative charge on the oxygen. All of those things tell you that the carbonyl carbon is the reactive electrophilic atom in this molecule. As a nucleophile attacks, we'll draw arrows like this. Notice that the pi star is above and below the plane of the carbonyl. You're going to see that carbonyls can be attacked from above or below. For those of you that just took 351 and still remember the words enantiotopic, the two faces of the carbonyl are actually enantiotopic. Attacking one gives you one enantiomer. If you make a stereocenter, attacking the other gives you another enantiomer. In any case, you'll draw arrows like this. That arrow from the 2 electrons on the nucleophile to the carbon indicates the formation of a new carbon nucleophile sigma bond. If we stop there, we'd have too many bonds to carbon, so we have to break the pi bond and the electrons go out onto the oxygen, okay? That's going to be the first step of most of these reactions with carbonyls. Now, carbonyl compounds vary in terms of how reactive they are. And what influences their reactivity is the identity of these R and Y groups attached to the carbonyl carbon. We're going to talk about that in a second. The other thing we're going to need to consider is the reactivity of the nucleophile. Fortunately, if you've taken 351, you know something about nucleophiles. We've talked before about how things that are negatively charged are generally good nucleophiles. That good nucleophiles generally are conjugate bases of acids with pKa's that are greater than 0. So we'll have a chance to review that, but you will need to remember and work on recognizing good nucleophiles. We're going to see that in some cases, either because the carbonyl compound is not reactive enough, or because the nucleophile is not reactive enough, that if we want to get something like this to happen, we're going to need to do something called activate the carbonyl compound. I guess before I do that, we can draw the intermediate that would happen if the nucleophile attacked the carbonyl compound. Notice that that carbon that used to be the carbonyl carbon is now going to be attached to 4 things. So we're going to switch from being sp2 hybridized at that carbon to being sp3 hybridized. Here is our new bond between carbon and the nucleophile. Here is the sigma bond between carbon and oxygen. The oxygen should now have a negative charge on it. And then the Y group is still going to be pointing out towards us, but angled down towards the bottom of the page. And the R group will be still pointing away from us, but now angled towards the bottom of the page. We call this the tetrahedral intermediate. But I'm just going to call it tetrahedral sp3 hybridized. In some cases, this will be an intermediate. In other cases, it'll be the product. There are other things that are going to happen after this point, but we're just talking about the first step right now. All right, as I said, some carbonyl compounds are going to need some help to be reactive, either because they themselves are not that reactive or because the nucleophile isn't that reactive. So let's talk about how to activate a carbonyl compound. There are a couple of strategies. One is Bronsted acid activation. And the second is Lewis acid activation. They're both sort of examples of the same thing. The idea here is that we're going to use either a Bronsted acid or a Lewis acid to make the carbonyl more reactive. Let's suppose we use a Bronsted acid. In this Bronsted acid activation, your carbonyl compound is acting as a nucleophile and is going to deprotonate the acid. If we were to look at this carbonyl compound, in general, the highest occupied molecular orbital of the carbonyl compound is going to be the lone pair on the oxygen. Okay, there are actually 2 lone pairs on the oxygen. You can think of them as equal in energy. It turns out MO theory tells you that they're not, but that's a result we are going to blithely disregard because it mostly doesn't tell us anything in this class. So the HOMO is one of the lone pairs on the oxygen. So what we're going to do is simple acid-base chemistry. The acid protonates the carbonyl compound, resulting in the conjugate acid of the carbonyl compound, which looks like this, and the conjugate base of your acid. This protonated carbonyl compound is called an oxonium ion, and I will refer to it as such, so just make sure you recognize that term. A little bit about the oxonium ion. Its pKa is around -2, maybe a little bit lower. So it's about as acidic as hydronium. So that tells you that if you want to do a Bronsted acid activation of a carbonyl compound, you want to use an acid that can protonate an oxonium ion. Okay? So that's, and the effect of, let's talk about why that activates the carbonyl compound. There's 2 reasons why. First, it lowers the energy of the LUMO. That's difficult to see without looking at MO theory. So instead, without the details of MO theory, so let's just actually instead use resonance as a concept. The oxonium ion has a resonance structure in which the oxygen is neutral and the carbon is positively charged. To get to that resonance structure, all you do is move the pi electrons from the carbon-oxygen pi bond out onto the oxygen. Notice that for a regular carbonyl compound, you can draw that same resonance structure, but in this case, the oxygen's negatively charged. The oxonium ion, by virtue of already being positively charged, you don't have to put a negative charge on the oxygen. There's no charge separation. Basically, protonation of the carbonyl to get the oxonium ion makes this resonance structure more reasonable, and it makes the carbonyl carbon more electrophilic. Okay? Yes?
Depending on the identity of the R group, is rearrangement of that carbocation possible? Or because of resonance, does the carbocation stay there for the sake of the R?
It's a good question. Is rearrangement possible? And the answer is there are such things, but not really, that we'll get to within the scope of this class. And you can think of it as a resonance stabilized carbocation, where the lone pair electrons on the oxygen are donating in to that positive charge, and therefore, yeah, generally no rearrangement. Okay. Other questions? Yeah.
So were you saying that it's mainly due to the contributions of that resonance structure there on the bottom that the carbon is more electrophilic?
That's right.
Okay.
Yeah, it's the contribution of this resonance structure on the bottom that makes the carbonyl carbon more electrophilic. The other way of reasoning through that is just to look at this and say, hey, I know the formal charge is on the oxygen, but oxygen didn't start suddenly being less electronegative than carbon. Oxygen's more electronegative than carbon. That's going to mean most of this positive charge should be felt on the carbon, and it is. Okay? Others? All right, real briefly, Lewis acid activation of carbonyl compounds. We won't see this too often, but it is a thing. Maybe actually we'll see it when we talk about how proteases work, but the idea here is you want something that's not a proton but still has space for electrons to go. So this might be coordination of ions or other molecules. I'll give you an example that won't make sense a lot at this stage, but we're going to come back to it a little bit later today. Here is a reagent called diisopropyl aluminum hydride, or no, diisobutyl aluminum hydride, sorry, got a little bit mixed up there, or dibol for short. And it's got an empty p orbital on the aluminum. And the way this reagent works is first, the lone pair electrons on the oxygen attack the empty p orbital on the aluminum. If you can't see that the aluminum has an empty p orbital, remember that aluminum's in the same column of the periodic table as boron. When boron's bonded to three things, sp2 hybridized, it's got an empty p orbital, same with aluminum. And that generates an intermediate that looks like this. It's going to look a little bit like the oxonium ion because the oxygen's got a positive charge on it. There is something that happens after we get to this point, but I'm going to defer on that to a little bit later when we talk about the reagent. But again, you see the same basic idea. Lewis acid or Bronsted acid activation of the carbonyl first have the lone pair on the oxygen doing something to create an oxonium ion where the carbon is even more electrophilic because you can draw a resonance structure that would put a positive charge on that carbon. Okay, yes?
Is that step not reversible?
Is this step not reversible? I put the reversible arrows here to indicate that this is acid-base chemistry. I'm not bothering here because as soon as this intermediate forms, there is something that happens. I'm just not telling you about it yet. Okay. All right. Let's talk about ranking carbonyl compounds in reactivity. There's so much to do. I haven't told you what happens to this oxonium ion. I also haven't told you what happens to the tetrahedral intermediate. All in good time. So let's talk about their relative reactivity. And to do this, we need to talk about what the Y group is attached to the carbonyl carbon. We're going to assume for now that the R group is something carbon containing. If the Y group equals, that's going to get old. I wonder how many days they're going to be grinding it, whatever that is. All right. So if the Y group is a hydrogen, the molecule is an aldehyde. If instead the Y group is some alkyl group or perhaps some other carbon-containing group, it could be a methyl group, it could be a benzene ring. This is what we call a ketone. Okay? An aldehyde has one carbon thing on it and one hydrogen. A ketone has two carbon things on it. Let's talk about the relative reactivity of aldehydes and ketones. Here is an aldehyde. Here is a ketone. We're going to see that aldehydes are more reactive than ketones. Ketones are still, understand that more and less are relative terms. We're just making the comparison with each other. Ketones are still decently reactive, but they're not as reactive as aldehydes. We can talk briefly about why that is. Again, a lot of our reasoning in terms of carbonyl reactivity is going to have to do with the resonance structure that puts a positive charge on the carbon. And we're going to ask, what's the difference between these two resonance structures? And what we're going to see is that carbons, what's the best way to talk about this? What we're going to see in general is that alkyl groups have electron donating properties. There are a couple of ways to reason through this. The first is to recognize that the carbonyl carbon is sp2 hybridized, and that the adjacent ketone, the adjacent methyl group on the ketone is sp3 hybridized. And then to recognize that owing to their increased S character, sp2 carbons are more electronegative than sp3 carbons. And therefore, the sp3 carbon should be able to share electron density with that electron poor sp2 hybridized carbon, okay? The proton is less able to donate electrons into that sp2 hybridized carbon, in part because it has fewer electrons associated with it. In the methyl group, you have all of these adjacent carbon-hydrogen bonds, each with electrons that can be that can donate through the sigma bonds into the carbonyl carbon. Okay, that's one reason. The second reason involves something called hyperconjugation, and I don't want to spend a lot of time on it at this stage, but I'll mention it just briefly. To show you this, we need to draw the carbonyl compound from the side. The R group is here. I'm going to draw the methyl group here. You'll have to understand, even though I'm using straight lines, that this carbon is sp3 hybridized tetrahedral. What I'm intending to show you is that the R, the carbonyl carbon, this carbon, and this oxygen are all in the plane indicated by this parallelogram. This carbon-hydrogen bond is pointing up above the plane, and these two are pointing down below the plane. I'm going to draw real briefly the LUMO, the empty pi star on the carbonyl carbon. That's kind of a cruddy drawing, oh well. Didn't get much better, oh well. So that's the empty carbon oxygen pi star. Adjacent to that empty carbon oxygen pi star, I have carbon hydrogen bonds. Oops. What I'm drawing for you now is the filled carbon hydrogen sigma bond that's adjacent to the carbonyl carbon. When you have a filled orbital in a molecule that's adjacent to an empty orbital, the electrons in the filled orbital can spread out slightly into the empty orbital, and electron delocalization is always favorable. So that makes the molecule more stable. It also makes the carbonyl carbon less electron poor. So what we're saying is that the electrons in that carbon-hydrogen bond are spreading out a little bit into that empty orbital. Okay? That allows them to move lower in energy. It has some other consequences that we'll revisit at a future date, but that's the second way in which alkyl groups are electron donating in character. We see that alkyl groups are electron donating because the sp3 hybridized carbon is not as electronegative as the sp2 hybridized carbon of the carbonyl, and so they can donate electron density in just through polarity. And then the second explanation is that you have alignment of the adjacent carbon-hydrogen filled orbital with the empty carbon-oxygen pi star, which also allows electron density to be shared with the carbonyl carbon. Yes?
So because they're electron donating character, that's why they're less reactive?
That's right. Things that donate electron density into the carbonyl carbon should make this positive charge less of a big deal and make it less attractive for a nucleophile to attack.
So is that a general trend, more electronegative, the less
is that a general trend? The more electron donating things you have attached to the carbonyl carbon, the less reactive? Yes. Good. Others? Yeah.
Does the hydrogen on the aldehyde have hyperconjugation?
Does the hydrogen on the aldehyde have hyperconjugation? The answer is no. If you compare the aldehyde, this is like the perfect storm. It's 8 a.m., you're taking OChem, and somebody's somewhere banging on stuff. I'm really sorry about that. But life is full of challenges and disappointments. So, if this is hydrogen, notice the only electrons surrounding the hydrogen are the ones in the carbon-hydrogen bond. There are no adjacent groups that could donate through hyperconjugation. Yeah. Okay. All right, so it turns out that the Y group can be a lot of different things besides just hydrogen and carbon. There's a ton of other options, and I want to just summarize a few. What I'm going to show you now, depending on what the Y group is, these are generally called carboxylic acid derivatives. And they involve often heteroatoms attached to the Y group, where the Y group is. So if the Y group is an OR group, then what we have is an ester. The squiggly line here indicates that we've attached whatever this is to the carbonyl carbon. Okay? If the Y group is a nitrogen, it could be any one of the following options. We're going to call that an amide. If it's a chloro, we're going to call that an acid chloride. If the thing attached to the carbonyl carbon is some kind of carboxylate, we're going to call it an anhydride. And then, of course, we can get much more exotic than that, especially in biological molecules. So if the thing attached to the carbonyl carbon is a sulfur, we're going to call this a thioester. And later on, you're going to see examples, especially in biochemistry, where the thing attached to the carbonyl carbon is a phosphate or perhaps something like this. We're going to call those molecules acyl phosphates. Okay? And again, we will be able to rank their activity, their reactivity, based on a couple of features. The first is going to be how much do these groups donate electron density into the carbonyl carbon. And the second will be to what extent are these groups good leaving groups on their own. Let's deal with the issue of their relative reactivity based on electron donation. All right. So to do this, I want to compare the acid chloride, the ester, and the amide. Okay? And I will tell you that the acid chloride is most reactive and the amide is least reactive. There are a few ways you can rationalize this. Let's deal with the electron donation rationale to begin with. Let's draw the resonance structure where the positive charge is on the carbonyl carbon. And then let's consider the ability of each of those Y groups to donate electron density into the carbonyl carbon. Notice that each of these Y groups has a lone pair on it. Okay? So each of them should actually be able to donate electron density into the carbonyl carbon via resonance. In other words, for each of them, I can draw an alternative resonance structure in which I take the lone pairs on each of those atoms attached to the carbonyl carbon, and I draw a resonance structure like this. Oops. Okay. Questions about how I got those resonance structures? I don't really like how I drew them, but we're going to see that the fact that the amide is less reactive than the acid chloride reflects the fact that this resonance structure here is a better resonance structure than this one. Okay, let's talk about why that might be. Why is this a better resonance structure than this one? Any thoughts? Go ahead.
Electronegativity.
Okay, electronegativity. So in what way? Can you expand on that?
Nitrogen is less electronegative.
Nitrogen's less electronegative than chloro. I think that's true. I don't remember exactly what the numbers are, but yeah, we can look them up. So that means that nitrogen should be what? More or less willing to share than chloro? More willing to share. And in general, nitrogen is a better electron donor, better electron donating group, or EDG, than chloro. Chloro is a poorer electron donating group, partially because of its increased electronegativity, also because of the increased size of chloro relative to nitrogen. The carbon-chlorine bond is longer and weaker. Chloro is less close. It's less able to donate electron density into the carbonyl carbon. Okay, how about the comparison of nitrogen versus oxygen? Why is this resonance structure for nitrogen better than this resonance structure for oxygen? Any reason to suspect oxygen is not as good of a donor as nitrogen? Oh, it was obvious, so you didn't want to say. Is that what was going on? Okay, that's fine. That's fine. I've taught plenty of Sunday school lessons where I asked similarly leading questions and got similar responses. So good. Yes, it tracks with the fact that oxygen is more electronegative than nitrogen and therefore a poorer donor. Okay? So you can use that as a way to rank the reactivity of carbonyl compounds. The other way you can do this is to consider the ability of that Y group when attached to the carbonyl carbon. Think about what it would be if it left Cl minus, OR minus, NHR minus. And this trend also tracks with leaving group ability. Do you see that the most reactive carbonyl compound has a Y group that is the best leaving group? You can tell that it's the best leaving group because its conjugate acid is a really strong acid with a pKa of around minus 7, I'm guessing. whereas the conjugate acid of the OR minus is an alcohol with a pKa of 16, whereas the conjugate acid of this negatively charged nitrogen is an amine, pKa 38. In other words, this trend also tracks with leaving group ability. If the Y group is a good leaving group, chances are the carbonyl compound is really reactive. And we can use this later trend to explain some trends in reactivity among some of the more exotic carbonyl compounds. As an example, if you wanted to think about an anhydride versus a thioester versus an acyl phosphate, you could do a little bit of thinking. All right, what is the Y group attached to the carbonyl carbon? Some of you are going to notice that with anhydrides, how do you know which one's the carbonyl carbon? And I'm going to say exactly, but for right now, just don't worry about it. Here are the Y groups. To think about the relative reactivity of these carbonyl compounds, let's draw the Y groups as they would appear if they left. Then we can draw the conjugate acid of the Y groups after they've left. Then we would look up in a pKa table, which you may not have here, but I happen to know the numbers, so don't worry about it. pKa of the carboxylic acid is around 4. pKa of the thioester, the thiol, is around 8. The conjugate acid of that phosphate is this molecule, which has a pKa of around 7. I think. I'll have to look it up. It's close to that. So you would expect the anhydride to be a little bit more reactive than the thioester. You'd expect the thioester and the acyl phosphate to be similar in reactivity. You're going to see in biochem that nature interchanges these two all the time. And when you see that, you're going to think, oh, that's perfectly reasonable. That makes sense. They're similarly reactive. At the same time, you could look at the anhydride and say, gee, I expect that to be not quite as reactive as the acid chloride. Why? Because the acid chloride's got a better leaving group on it. Okay? Questions about that? Okay. We need to get to some chemistry. I want to show you now what can happen to this molecule here after the nucleophile attacks, this so-called tetrahedral molecule. What can happen next? All right, let's scroll down. And the answer is, it depends on whether the Y group is a good leaving group or not. So let's look at the list of Y groups that we have. We have ketones and aldehydes. Those aren't good leaving groups. H minus, CH3 minus, terrible leaving groups. Conjugate acid pKa's of 35 or above. So we don't expect them to leave. So let's scroll back down and let's do an example where we have a nucleophile attack an aldehyde or a ketone. Let's just do an aldehyde. We're looking at it from the side. I'm going to be pretty general. We're just going to say, here's the nucleophile. Oops, and I meant to put hydrogen there. Attack the pi star, break the carbon oxygen pi bond. make a new bond between nucleophile and carbonyl carbon. And there you are stuck because nothing can happen. Unless, of course, the nucleophile is a good leaving group itself. If the nucleophile were a good leaving group itself, it might be possible for the lone pairs on the oxygen to kick the nucleophile back off. That happens, we will see that happen. In such cases, this first step might be reversible, okay? But for our purposes today, let's just imagine that the nucleophile, the bond between the nucleophile and the carbon is quite stable. The nucleophile is not a good leaving group. So once the nucleophile attacks, there's nothing else that can happen. You're sort of stuck there, and this is what we call a nucleophilic addition product. Nucleophilic addition because we have added a nucleophile to the carbonyl compound. Okay? We're going to see that a lot with aldehydes and ketones because there is no good leaving group. Yeah?
You talked about how this has conjugate acids of pKs 35 and above, even though an amide has about 38. Are we always supposed to consider amides as leaving groups? And this one as leaving groups?
Yeah, you asked, the question was, over here we talked about the amide as a leaving group. Amides are not very reactive. We will see examples of chemistry where the amide, the negatively charged nitrogen does end up leaving, but only under the most strenuous of conditions. It's really quite difficult. And it's often because there's something else that can happen to this immediately to stop it from being negatively charged. We will, only in biology will we see H- leave as a leaving group. And then it's only because it's handed off directly as directly to something else. Okay. Let's do an example where the Y group is a good leaving group. So let's choose the best leaving group. I'm just going to label this if Y equals H, not a good leaving group. Now let's let Y equal Cl, where Cl minus is a good leaving group. And let's see what can happen there. Again, we'll zoom in. Oops, I think. Here is Cl. Again, the nucleophile attacks the pi star, making a new carbon nucleophile bond, and the leaving group leaves. That generates a new sigma bond, breaks the carbon-oxygen pi bond. Oops. And we have this, which I'm now going to call a tetrahedral intermediate because it's only an intermediate. We are not stuck. This is not the product. It looks exactly the same as above, but the contrast is our Y group here was H, basically H minus and couldn't leave. Here the Y group is Cl minus and that can leave. That is a good leaving group. You have here a leaving group, and then at the beta position adjacent to that leaving group, you have a negative charge. This is an example of a situation where you can do an elimination reaction. This is analogous to an elimination reaction that you saw in 351, where a base removes the proton. Here is the alpha carbon that has the leaving group. Here is the beta carbon. A base removes a proton from the beta carbon. Negative charge builds up on the beta carbon, then kicks down and kicks the leaving group off. That's an example of a so-called beta elimination reaction. And that's E2 was your first ever example of that. Here's another. We don't have a proton on that adjacent beta position, but we do have a negative charge. And so electrons can kick down actually into the carbon chloride antibonding orbital, the sigma star, and then break the carbon chlorine bond, and chlorine can leave. And then our product is as follows. Then we reestablish the carbon oxygen pi bond, and we now have what's called a substitution product via two steps. The first step is addition. The second step is elimination. Nucleophilic addition of the carbonyl carbon at the carbonyl carbon to give you a tetrahedral intermediate, followed by beta elimination, leaving group leaves to give you your substitution product. Cl minus is the leaving group. We have swapped out the nucleophile, and the nucleophile has replaced the leaving group. Okay? Those are the two types of carbonyl reactions you will see. Everything between here and chapter 16 is going to involve these steps. Yeah?
The addition product above that has the negatively charged oxygen, is that going to stay there, or do we expect like aqueous work?
Great. Yeah, good question. Thank you for bringing that up. So the addition product that we're stuck at is negatively charged. What happens next will depend on the reaction and the conditions. But for the most part, at the end of a reaction, we will do what is called aqueous workup. If you are taking the 353 organic lab, you will do this a lot. This basically involves taking your reaction mixture, usually in a little flask that is stirring in some organic solvent, and you literally dump water in. And it should be no surprise to you that if I dump water in, that negatively charged oxygen, in particular if there's an excess of water, is basic enough to remove a proton from water to give you the corresponding conjugate acid of what we drew above. So yes, you're right, this is the final addition product. Your text will try to be pretty obvious about this. Often your text will include the water as a second step, nucleophile in the first step, water as a second step. Understand that all they mean by that is aqueous workup to protonate the negatively charged oxygen. However, if you read papers in organic chemistry, often they'll put that they did aqueous workup in the procedure, but they're not going to write that down as a separate step, because in their mind it's not a separate reaction. It's just part of the synthetic step that they were doing. Okay, good. Other questions? Yes?
So if Y is a good leaving group, will the nucleophile always have the same procedure as the leaving group?
Right. If Y is a good leaving group, is the nucleophile always going to be? I did that. I'm sorry. I was just being cute. You're right, actually, that this is not a stereocenter. The nucleophile, if we flipped it over, could be in the other position. So yeah. I left it there just to make it absolutely clear that we were doing a substitution reaction. But you're right. The nucleophile could be either here or there. And actually, it's the same molecule if you flip it over. Understand that if this product, let's go back to the just addition where Y is not a good leaving group. Notice that we made a stereocenter here, right? If I make a stereocenter, remember that the pi star is above and below the plane of that carbonyl. I have to get both enantiomers. I get one enantiomer from attack from above. I get the other enantiomer from attack from below. And so I'm just going to use the plus or minus symbol here. That's an old symbol from the days of doing optical rotation experiments, which people still do on chiral molecules. That indicates you have both the the clockwise and counterclockwise rotating chiral molecules present in equal amounts. It means you get a racemic mixture of enantiomers. Okay. So we have our work cut out for us, because what we're going to do now is focus in on the we're going to focus in on using really strong nucleophiles to do chemistry with aldehydes, ketones, and then some of the carboxylic acid derivatives. Now's probably a good time for a break. If we take 10 minutes, you'll have to go super fast in the second half of the class. I propose we take 5. So go ahead and take 5, and we'll pick it up again when you're back.